Alright, now we're going to talk about a few more tests to determine the convergence of a series. You might recognize some of these tests from your days in calculus. This is the alternating series test. Let's say you have a sequence of numbers. Let's let them be non-negative. And when I say numbers here, I obviously mean real numbers, such that the sequence decreases to 0. So by this here, I mean, firstly, that the terms do go to 0, but also that the terms are decreasing. If these requirements are met, then the alternating series from 0 to infinity minus 1 to the n converges. Now before I provide a proof, let's think about what this means. If you look at the following sequence, 1 over n, that's 1, 1/2, 1/3, 1/4, and so forth. We have seen before that the sequence here does converge to 0 and that it is decreasing because 1 over n plus 1 is smaller than 1 over n for every n. So the requirements here are met. I should mention, of course, that this non-negative real numbers we also have that 1 over n is greater than 0 for every n. Hence, minus 1 to the n times 1 over n would be 1 minus 1/2 plus 1/3 minus 1/4 and so forth converges. And we'll be able to say a little bit more about where the value to which it converges resides. But for now, let's actually provide a proof. We're going to let Sk represent the partial sum of the series from 0 to k. So what do we have? S0, that is just A0. S1, that would be A0 plus minus 1 to the 1 minus 1 times A1. So that's minus A1. S2 is A0 plus minus A1 plus A2. S3 would be A0 minus A1 plus A2 minus A3. S4 would be A0 minus A1 plus A2 minus A3 plus A4. S5 would be A0 minus A1 plus A2 minus A3 plus A4 minus A5 and so forth. Now look at this. S0 compares to S2 as follows, right? This little term here is S0. So this is the same as S0 minus A1 minus A2. And if you look at S4, the first three terms are the same. So this here is S2, and then you have minus A3 minus A4. In general, and this wouldn't be too hard to show, you could show it by induction. S2n is going to be equal to S2n minus 2 minus A2n minus 1 minus A2n. This is true for every n. If you look at the odd index partial sums, you get something of a similar nature. S1 is A0 minus A1, great. Then we have S3 as A0 minus A1, which is S1. Now we have a plus term here, plus A2 minus A3. S5 would be S3 plus A4 minus A5. And again, by induction, in general, you can show that S2n plus 1 would be equal to S2n minus 1 plus A2n minus A2n minus 1 for every n. Now, because the sequence is decreasing, we know that A3 is going to be larger than A4, for instance. That A1 is larger than A2. So what we are doing here is we're removing a positive quantity, or at least a non-negative quantity. So in general, S2n is going to be smaller than S2n minus 2. For the odd-numbered partial sums, you get the same argument. This is positive. So if I take Sn2n minus 1 here and send it to the other side, I will get that S2n plus 1 minus S2n minus 1 is equal to A2n minus a2n minus 1, which is positive, and so I can conclude s2n plus 1 is greater than s2n minus 1 right here. If I use the even numbered terms, so let's say I replace n by 1, I get that s0 is larger than s2, and s2 is larger than s4, and s4 is larger than s6, and so forth. And if I use the odd numbered partial sums, so let me pick n equal 1 here, for instance, s1 is smaller than s3, is smaller than s5, and so forth. Now, the way I'm writing this here gives you the impression that this is a chain of inequalities, but the reality is I've written two chains of inequalities here. Like, we would need to show that all of the odd numbered partial sums are smaller than all of the even numbered partial sums before we can actually combine those into one chain of inequalities. Is it the case that every even numbered partial sum is larger than every odd numbered partial sum? Well, let's go back and look at the thing for a bit. S0 is A0. S1 is A0 minus A1. So we definitely have that S0 is greater than S1. Right? Again, this is only true because the number we're removing here is a positive number or non-negative number by assumption. What about the rest of the deal? Well, S0, S3 here is S0 minus A1 plus A2 minus A3. If this quantity here is negative, then we will have that S3 is S0 plus a negative number, hence S3 will be smaller than S0. Is that the case? Let me rewrite this slightly differently. S0 minus A1 minus A2 plus A3, and so we're looking for this quantity here to be positive. But the sequence of ANs is decreasing, so A1 by definition is greater than A2, and so A1 minus A2, that's going to be positive. And then if I add an A3 to it, it's going to be greater than or equal to 0 plus A3, which is greater than 0 because the sequence is a sequence of non-negative value. Alright, so this thing is positive, hence the whole thing is negative, and so we would conclude here that S3 is smaller than S0. In fact, it's not too hard to show that any odd numbered partial sum is smaller than S0. So we know this is true for every n, and then you can actually show that this also has to be true if you replace S0 by some of the other even numbered partial sums. So there's still some work to do, but you can show, that's the main takeaway here, that S0 is greater than S2, is greater than S4, is greater than S6, greater than all of the subsequent even numbered partial sums, and all of these are greater than the odd numbered partial sums. Now S0, we know what it is. It's A0. S1, we also know what it is. It's A0 minus A1. So what do we have here? Well, if you look at the sequence of even numbered partial sums, we've shown here that it is a decreasing sequence, but we've also shown that it is bounded below i.e. 0 minus A1. And so if we use the monotone bounded convergence theorem, we conclude that the limit of the even numbered partial sums exists. You can do the same thing for the sequence of odd numbered partial sums. They're increasing and they're bounded above by A0, so the limit of S2n minus 1 exists. So both of these exist, and so in particular the limit of their difference has to exist according to the theorem on the operations on sequences. But we know what S2n minus S2n minus 1 would be, right? S2n is the alternating sum all the way to this, and S2n minus 1 is the alternating sum all the way to the term just before it. So if you subtract S2n minus 1 from S2n, you will get exactly A2n. Here, it's equal to the limit, and n goes to infinity of A2n. So the limit of all the even numbered terms of the sequence. This limit exists because we know by hypothesis that the ANs converge. So the limit of A2n is 0, and so the limit of this difference here is 0. Now it doesn't tell us what the limit of the partial sums would be, but the limit of the differences is 0. In particular, what this tells us is that the limit of the even numbered partial sums is the same as the limit of the odd numbered partial sums. Well, we conclude from that the alternating series converges. And we can say a little bit more, although that's not part of the statement. According to this, the limit's got to be here somewhere. So in particular, it is going to be bounded by S0 and S1. So if the limit of the series is L, it's going to be found between the first term and partial sum once you've added the second term. If you wanted to estimate the value of the alternating harmonic series, we just compute some of the partial sums. S0 is 1, S1 that's 1 minus 1/2. So right off the bat, we know that the true value has to lie between 1 and 1/2. If we call the value of the series L, what we know is that it has to reside between 1 and 1/2. We can go even further, right? It doesn't just reside between S0 and S1, it also resides between S2 and S3. So S2 would be 1 minus 1/2, so 1/2 minus or plus 1/3, and then S3 would be equal to 1/2 plus 1/3 minus 1/4. And you could get this to be as accurate of an estimate as you want by, well, just going through enough terms in the sequence.